Okay, very good afternoon to one and all. We'll start our today's session. Okay. So last class we completed our discussion regarding our DES algorithm, right? So today we move on to next topic, that is principles of pseudo random number generation with respect to block ciphers. Okay, with respect to block ciphers, right? With respect to block ciphers, because last module we had a discussion about what do you mean by a pseudo random number and different ways how a random sequence as well as a pseudo random sequence can be produced, right? So these are the three ways where you can able to produce a random and pseudo random sequence, starting from TRNG, that is true random number generation. Then we have PRNG, which makes use of seed value as input and it takes a feedback also. Then we have PRF, that is pseudo random function, which has an extra context specific values, right? So these are the three different variants of pseudo random number generators. Okay, now we can also able to apply, that is use our block ciphers, that is modern day block ciphers as PRNG, that is pseudo random number generators, to generate random sequence. Mostly this will be used for creating session keys, like for example our cipher keys or any key generation process also can be applied by using block ciphers as PRNG. Right, there are two different approaches where you can able to actually here there's a typo, this PRNG. Okay. Can be used to build a PRNG, that is serial random number generator. One is called counter mode, which is shortly called as CTR, then output feedback mode called OFP. Right. So if you see these two variants, that is CTR and OFP, okay, it comes under ANSI standard H9.82 called random number generator. Okay. So if you see mathematically how this random number generation works on for a counter mode. So this HI is something but output, random output for ith iteration. Okay. So this is obtained fine by using an encryption algorithm. This E suffix K is a block cipher. Okay. It is a block cipher using K as a key, right? It's encrypting a value. This V suffix I is nothing but your seed value here, right? For the process of obtaining this random sequence, you are using any block cipher. It can be your AES, DES, any block cipher technique, any fiestal, non-fiestal cipher, anything you may use, right? Whereas in output feedback mode, if you see the difference here, your output is same, the encryption algorithm is same, but here the input for the algorithm is nothing but the previous output. It's like a feedback output. Our previous output is given as the input, right? So that's why the name called output feedback mode. So if you see how this works on in a CTR mode called as counter mode, right? So here you will be having a seed value. Okay, seed value will be a block, okay, of a fixed size. For example, if you are using a DS algorithm, okay, the seed value will be 64-bit. Or if you are going for AES, this will be 128-bit, right? And the key size based upon your encryption algorithm, key size also vary. So for first iteration, okay, you'll be supplying with the seed value and you'll be getting a random sequence. Okay, just assume some random sequence you obtained. Okay. Then after first iteration, this seed value is incremented by 1. That is an XOR operation. 1 is going to be XOR with the seed value and the next value is going to be obtained. Then next and goes on. Like this, the entire sequence is going to be generated by by incrementing the seed value by value 1. This is how your counter mode works. Then comes your output feedback mode. Here the seed value is initially fed and the output is obtained, but it is updated. The seed value is updated with the, for example, if you have got x2, the previous output means the previous value, that is x1, will be present here. Okay. So it is like a feedback process how the how this output feedback mode works on. So here we obtain a random sequence, which sequence of 256 bit. Okay. And we took two random 256 bit sequence from the website called random.org, where you can able to get all the random values. Okay. Why we are taking from this one, since all the random sequence which are present taken from this website will have approximately 50% of ones and 50% of zeros, satisfying the property of randomness. Right. So out of this 256 bit seed, 124 we have ones, that is approximately 48%. So using this Q, I mean this key and the seed value, once if you operate on output feedback mode, okay, the fraction of one number of bits for each and every iteration. So this is for first iteration, second, third, and goes on. You can able to see the fraction of bits here of 57% or once 51%, 47, 50, 47, 49. So roughly it comes under 50%. At the same time, this is for first iteration. The bit difference between first iteration and second iteration is 52%. Nearly 50% is totally, approximately 50%. It is differing from each and every iteration. Right. So the sequence is approximately 50% different, so that you can use this one. For example, if you have a seed value, then you'll be using this one as a seed for the next block, this one as a seed for the next block, so that they are totally 50%, they are totally differing from the present output with the previous output, right? And the same key and seed value is used in counter mode. Okay, even though if you are you're getting the same fraction of bits, roughly 50%. Even if you increase your seed value by 1 also, you can able to see the fraction of bits that are matching with the preceding block is also only 50%, roughly 50%. Okay. So these are few examples of your serial random numbers using serial random number generator using output feedback mode and the CTR mode. Is it clear, guys, regarding these two modes? If it is clear, raise your hand. If anyone have any doubts, you can ask me. Very simple concept. Right. Now we want to one of the famous pseudo random number generator, which employs one of the famous block cipher technique called DES. Actually, we used to call it as a triple DES algorithm. Okay. It's coming under a standard called it's 9.17. Yes, okay, it's full stop. It's 9.17 is the standard. Okay. So here, this application, this serial random number generator, mainly used in financial security applications. Wherever you need some random sequence for financial security applications, still in present day, we are using this standard called triple DES algorithm. That is, this EDE is nothing but your DS algorithm. So this is your DS1, DS2, and DS3. We'll be using 3 DS algorithm. I'll directly go into this one. Right. So here I'm using a key called K1 and K2. There are two key values. I'm able to see. Sorry. We have two key values K1 and K2. And we have two inputs. Apart from this key, we are having two inputs called, this is date and time for that at that ith iteration. For example, if your I value is 2, at that instant, what is the date and time? Your date will be same if you're doing multiple iteration at the same day, but the time will vary at least in the level of microseconds, right? So here comes the natural source of randomness coming into picture here. Okay, date, time, and here this is nothing but your seed value, right? Initial seed value, which will be a 64-bit since you are using AES algorithm, sorry, DES algorithm, right? So these are two inputs, and you're going to get two output. One is the random sequence, which is the required part in PR sequence, serial random sequence, and we are getting another value called VI plus 1, which is nothing but the next seed value, which will be used as input in the next iteration, right? So how this works on, for example, I can able to write the output Ri. How I can able to write here because if you are using this one D1, okay, so here RA is obtained from the signal flow, that is a data flow from this first D1 itself, because it's going to get a key called K1 K2 and input of DTY, so DTI, that is your date and time. So I can able to write this one as D1, which is going to get input of K1 K2 and DTI, right? This is one. So this whatever the output which I obtained here is traveling here and it's waiting here. Okay, now I'm going to supply with the second input, that is your seed value, which is simply XOR operation, right? So this entire thing is again XOR with VI, right? Now this one is coming here as an input here. It is also getting the key value here for the second DS algorithm, right? So this entire thing is again encrypted. Sorry. Again encrypted with a key called K1, K2, right? In this entire key with my second DS algorithm to give me the output of RI. Right, the same which is explained here. They use the general term called EDE, but to be specifically speaking, I renamed this one as the second DS algorithm. This is my first DS algorithm. Right. So if you see this one, that is the output of seed value, it is getting added with the output which is obtained from first DES algorithm, which is traveling here, and your feedback value, that is this RI. So what they did in the sense, whatever output you obtained here at this point, so I can write my A plus one such thing, but your RI, whichever you obtained, second, sorry, RI, which is obtained here, it's solved with output which obtained from this one, that is from K1, K2 and DTA, right? And this entire thing is again encrypted using my third DS algorithm. So D3 of this one, comma, again using the key K1 and K2. That's what explained here, right? So this is nothing but your D1 again, and this is your D3, and all the keys K1, K2 are same. Right. So this is how the data flow is going to happen in ANSI X 9.17. Right. Is it clear, guys? If anyone have any doubt in this part, you can ask me. Okay. Then I will move on to the next topic. Right. Now we move on to next one called modern stream ciphers. So till now, whatever we just discussed is based upon block ciphers, right? All our starting from product ciphers, fiestal ciphers, non-fiestal ciphers. Then we came across DES algorithm, AES algorithm, then zero random number generator using block ciphers. Now we move on to modern day stream ciphers. So we already had a detailed discussion about what do you mean by a stream cipher and how it differs from our block ciphers, right? So here the entire encryption is like one-to-one mapping. That is, if you have a P2, there is a plain text second character will be mapped to second character of my ciphertext using a second character in the key. So here the plain text size will be equal to ciphertext size, which will be equal to again the size of the key. If I have n bits for plain text, I will be getting same n bits for ciphertext using n bits of key. Right. So there are two different classification or two ways where you can able to classify our modern stream ciphers called synchronous stream cipher and non-synchronous stream cipher. Okay, whatever I just said, the stream size will be same here. Right. So if you take a synchronous stream cipher, the key will be independent of the plain text or ciphertext. That is, we don't get any input, or we won't take anything from our input, or from our plain text or cipher text to generate the key. So here it will be totally using any random sequence generator, separate random sequence generator, which will give me exact same number of bits of a plain text size. If I is equal to 10 means, that is 10 bits means, I'll be getting 10 bits of random sequence, which will be used as a key. And the same random sequence will be shared with the receiver end by using some key exchange protocol or key exchange channel. And this key exchange protocol we'll discuss in the next, the next module actually. Right. So separate topics are coming under key exchange protocol, how we can able to securely exchange the keys. Right. So that both transmitter and receiver will be using same key at the for encryption as well as for decryption. Right. This basic step here, the simple process of encryption algorithm is nothing but a simple XOR operation. That is, whatever your plain text is going to come in as a stream of sequence will be XOR with the random sequence generated here, and I'll be getting my ciphertext. Okay, and which will be transmitted here. Which if you again XOR with the same bit, I can able to retrieve back the plain text back. Right. This type of operation is called one-time pad operation. Right. There is one-time padding is done here. Right. So now I have a question which will test your understanding of one-time pad cipher. This is the one-time pad cipher. Right. So here they ask you what will be the pattern of the cipher text of a one-time pad cipher. Okay, for these 4 different cases. First case, okay, and assume that in all these cases I am having a key k is produced as a random sequence. Okay, it's a random number. It is a random number. So first case they are saying the plain text is made up of n number of zeros. So I am having plain text full of zeros plus the key plus in sense it's a operation of random number. Okay. And they are asking how will be the pattern of the ciphertext. Can you people tell how the ciphertext will look like? Use chatbots or you can unmute it. The only clue is here the plain text is full of zeros. That's all. Yeah, yes, Kashish, you're correct. Your ciphertext will be same as my key value. Right. Second case, they're saying plain text is full of ones. Then what will be the ciphertext? How it will look like? Will look like if zeros, it is a key, right? If it is one, it will look like a complement of key, right? So, like what if you're getting the same key here? In this case, whenever your plain text is made up of one alone, and again your key is a random sequence, my ciphertext will look like a complement of my key. Now the third scenario, here the plain text is made of alternating number of zeros and ones. Okay. Now you want to answer me whether the ciphertext will be a random sequence or it will have some pattern in it. Whether it will be a random sequence or it will have some kind of patterned version of ciphertext. You can use chat. Yeah, some pattern will be there because it is an alternate version of ones and zeros. So the key will be coming as first K1, K2 complement, K3, K4 complement and goes on. Whereas about last one, they're saying the plain text is full of random, which means then your ciphertext will also be a random sequence. Right. Just the same thing is explained here. Now we move on to one of the famous synchronous stream cipher called feedback shift register based ciphers. Okay. How many of you came across a term called shift register or feedback shift register? Can you raise your hand? I hope you people have now studied under digital electronics. And only one. What about others? At least heard of the term called shift registers? How many of you have heard of the term? So here what it will do in the sense it will take input value from certain seed value, okay, and based on the feedback function, this F will be some mathematical function is going to manipulate the inputs B0 to Bm minus 1, which is taken from these boxes. Okay, it will manipulate something and an output will be produced from this one. What this output will do in the sense it will shift each and every value present inside the box to one bit towards the right, so that the B0 will be taken out as output here. For after first iteration, for second iteration, next bit will come out. Third, next bit will come out. Okay. For example, here they are saying create a linear feedback shift register with the 5 cells. Okay. And they are providing the feedback function as B5 will be equal to B4 XOR with B2 XOR with B0. First clue is nothing but here to create the shift register is using 5 cell. So you will be having cells, 5 cells starting from B4, B3, B2, B1 and B0. Right, this is the 5 celled version, right? And here B5 is nothing but the output of my feedback function. What they said is it will be a XOR version of B4 with B2, B2 with B0, right? So B4 is taken, B2 is taken, and B0 is taken, and all the three are XOR, and the output is fed back as a B5 value, so which will be pushing everything towards outside, right? So here they are saying that if Bi is equal to 0, so Bi in the sense if any value which is I mean,
Sir, isn't B5 the output value? I mean, why is B5 going back and be pushing B0 as the output?
actually B5 this one is nothing but a feedback function. That is what is going to happen inside this box. We already saw the feedback shift register. The function will look like this one. Bm is here. Here comes Bm minus 1, B2, B1 and B0. So whatever the output which is coming from the feedback function will be replacing Bm minus 1, right? So that B2 will be replacing B1, B1 will be replacing B0, and B0 value which is present at that moment will be taken as the output value here. So in this case, our Bm, okay, this is our m is 5, okay, this is m minus 1 is 4, m minus 1 is 4, then comes here 3, 2, 1 and 0. Is it clear?
So in linear feedback system, always B0 will be the output.
Yeah, B0 is the output, yeah, I'm saying B0 is output only. This B5 is not output, actually this is not output, this is nothing but a feedback function. That is output of my feedback function is nothing but this one. But output of my entire register I'm speaking about this one. This result, okay, instead of saying output, I can say the resultant of a feedback function is B5 and the output of the register is nothing but a B0.
Okay.
Is it? We will see an example so that you'll get a clear picture. So here you can able to see that you're asking again create a linear feedback shift register with 4 cells and they given the feedback function as B4 will be equal to B1 XOR with B0. Right, so this is how so here they made it into entire box. Here you can able to see the output here coming from B0. Is it clear now? This diagram maybe will make you
Yes, sir.
feel, yeah, right. So here initially they are supplying the seed value. The seed value they gave us 0001 binary value. So this will be taking 0001. Okay, and they asking to go for 20 transitions. So 20 times you have to perform this key generator. So the first step, this is the initial value. First step, I'll be getting 0, 1. If you XOR, I'll be getting B4 as 1, right? So after first iteration, this 1 will be coming and sitting here, next 0, 0, 0, and this one will be pushed as output value and will be coming out as 1 here. So like this, you can able to see here. So after first iteration, okay, 1, 0, 0, 0, it was initial value. Then we got 1 as output here, right? Next, I'm getting this B4 as this one. I mean, one second. First step, we XOR this two, right? And the output is pushed. I mean, output is pushing here. So my B4 value is here, which came as 1. So 1 is pushed here, 0 is pushed here, this one is pushed here, and here 1 came as output. So this is repeated for 20 repetition, right? So this is only a random sequence generation only, right? So if you see the key stream, suppose if we are using this stream ciphers to produce like a key kind of thing, you can able to see after 15 bits in the previous example, there is a repetition of the pattern. Okay, whenever you're using linear feedback shift register, so here you can able to see I'm having 1, 0, 0, 0, 1 and goes on. After 15th thing, again I'm getting the repetition 1, 0, 0, 0 and goes on. So after every 15 bits, the repetition is coming. So it will act as a zero random sequence. Though this 15 random, but this 15 bits are going to be repeated for after every 15 times. Right. So it is called as a zero random number sequence alone. We can't able to call them as a random sequence. So we can able to find the maximum period of repetition using this expression. That is how many number of your cells you are going to use or the seed value size will decide here. For example, in the previous one, the seed value size is 4 bit. So 2 power 4 minus 1, that is we got 16 minus 1, 15. Right. So this is how your synchronous stream ciphers works on with respect to linear feedback shift register. Okay. Then we have non-synchronous ciphers. So non-synchronous ciphers is nothing but the key will be depending upon either plain text or cipher text. And we can also make use of our the CTR mode to act as a stream cipher also. Like how in the sense you can use your counter mode in the, as a key generator. That is, you have your initial value, okay, seed value, which will be incremented after every iteration, and using some one of your block ciphers. As we already saw, we can use our block encryption or AES or DES algorithm here. Then you can able to produce the streams of ciphers from each and every bit. Right. Then accordingly the same thing will be used at the receiver end also. And also you can make use of your output feedback mode also. But here the only issue is nothing but the output which will be produced here will be, for example, here you have R number of bits for plain text. The key should be also be R number of bits. But the output produced here will be totally of R plus n number of bits. So that leftmost part R number of bits will be taken for the key and the remaining part n bits will be fed back for the next iteration. And the same thing can be used at the receiver end also. Right. So this is all about stream ciphers. So anyone have any doubt in this part? If it is clear, you can raise a hand. Okay. So with this, we'll wrap up today's session. So because